In this video, we are going to look at reactions of ethers. Ethers, just like alcohols, are considered to be organic derivatives of water. So, formally, we can consider that in an alcohol, one hydrogen of water is replaced by hydrocarbon, and in an ether, both hydrogens of water are replaced by hydrocarbons. This difference makes ethers considerably less reactive compared to alcohols. And in fact, ethers, because of their relatively low reactivity, are common organic solvents. So, for example, while alcohols are typically activated by conversion to sulfonate esters, as shown in the first equation, such reaction does not work with ethers. An attempted reaction with an ether gives oxonium ion, but since corresponding oxonium ion does not have a proton, it is unstable and reverts back to starting material, starting ether, and starting chlorosulfonate. So, for that reason, ethers are not readily activated by reagents that typically activate alcohols. Ethers do undergo cleavage reactions with rather vigorous reagents. So, for example, an ether can be cleaved upon treatment by hydrogen iodide, concentrated hydroiodic acid, and that results in formation of alcohol and iodoalkane. Or the same reaction could be carried out with hydrogen bromide or hydrobromic acid, concentrated hydrobromic acid, and then products are corresponding alcohol and bromoalkane. An ether has two substituents on oxygen. If at least one of those two substituents is either secondary or tertiary carbon, then reaction of cleavage of ethers proceeds through SN1 mechanism. And here is an example. Tertiary butyl methyl ether upon reaction with hydrogen bromide in an SN1 reaction gives tertiary butyl bromide and methanol as reaction products. Reaction mechanism proceeds through initial protonation of the oxygen. So a proton from hydrogen bromide is added to oxygen, protonates oxygen to give corresponding oxonium ion. And then in the second step, oxonium ion leaves, or carbon-oxygen bond is broken in such a way that tertiary carbocation is generated. Obviously, tertiary carbocation is stable, so methanol leaves to generate tertiary carbocation, and in the final step, nucleophile bromide anion reacts with tertiary carbocation to give tertiary butyl bromide as the other product. So at the end, reaction products are a molecule of methanol and tertiary butyl bromide. You can see from this example that when ether is unsymmetrical, the more substituted carbon, one that gives more stable carbocation, will give rise to alkyl halide as reaction product, while less substituted carbon ends up as alcohol as reaction product. Here is another example. So, unsymmetrical ether with one of the rather complex substituents, so cyclopentyl ring, secondary carbon, and the other substituent is simple methyl group. So reaction with hydrogen iodide results first in protonation to give corresponding oxonium ion, and then loss of methanol gives secondary carbocation. In this case, secondary carbocation undergoes a rearrangement to more stable tertiary carbocation. Remember that when carbocations are reaction intermediates, rearrangements are common, and whenever secondary carbocation is reaction intermediate, always check for possibility whether it could rearrange into more stable tertiary carbocation, as in this case. So rearrangement to more stable tertiary carbocation occurs, and then in the final step, tertiary carbocation combines with nucleophile iodide anion to give the final product 1-iodo 1-methyl cyclopentane. So in this case, products are rearranged alkyl iodide, 1-iodo 1-methyl cyclopentane, and a molecule of methanol. If both substituents on oxygen are primary or methyl carbons, then reaction cleavage of ethers proceeds through SN2 mechanism. Here is an example of ethyl methyl ether. So upon protonation, intermediate oxonium ion reacts in SN2 reaction. Now in SN2 reaction, less substitute carbon. So methyl, rather than primary, reacts in backside attack, typical SN2 attack, backside attack, in this case with iodide anion as a nucleophile to give the final reaction products. Products are ethanol and iodomethane. Note that unlike SN1 reaction, now selectivity is opposite. So less substitute carbon now gives rise to haloalkane or alkyl halide, while more substitute carbon ends up as alcohol. Here is another example, and in this case we have a benzylic ether, actually benzyl ether. So this is benzyl propyl ether, and that ether reacts with hydrogen iodide to give a benzyl iodide and propanol. In this case, benzyl iodide is formed because those compounds, remember benzylic and allylic compounds, react at very fast rate in SN2 reactions. That's because of the stabilization of the neighboring transition state by the pi system. We have covered that in chapter 12 when we covered SN2 reactions. Now, if we use two equivalents of hydrohalic acid, then both compounds are converted into corresponding alkyl iodides. That's because second equivalent reacts with resulting alcohol to convert that alcohol into corresponding iodoalkane, in this case iodopropane. We covered reactions of alcohols with hydrogen iodide and hydrogen bromide earlier. And at this point we should look briefly at push-pull effect, why these reactions occur. So cleavage of ethers occurs when they are treated with hydrogen iodide or hydrogen bromide, or their aqueous solutions, concentrated solution of hydroiodic or hydrobromic acids. But reaction does not work with hydrogen chloride, and that's explained by push-pull effect. So to cleave an ether, it is not enough to convert oxygen into a good leaving group by protonating it or complexing it with some other strong electrophile. In addition, a strong nucleophile is required. And the role of electrophile that complexes or attaches to oxygen is to pull oxygen or the leaving group, nucleophile, out of the molecule. So that would be what we call pull effect. While the role of strong nucleophile is to push it out. And in reaction of unreactive molecule, such as an ether, both pull by electrophile and push by nucleophile are needed. And so this is called push-pull effect. In case of chlorine or hydrochloric acid, chloride anion is not nucleophilic enough. It is not a nucleophile that is strong enough to push oxonium ion, to push alcohol out of the molecule. And so that push part of push-pull effect is missing, and so the reaction doesn't occur. A class of ethers that play important role in organic synthesis and organic chemistry in general are epoxides or oxiranes. Epoxides or oxiranes are ethers that contain three-membered ring. So they are cyclic ethers in which a three-membered ring contains oxygen as one of the ring atoms. And related compounds are four-membered rings with one oxygen as a ring atom. Trivial nomenclature names such compound basic three-membered ring C2H4 oxygen, C2H4O as ethylene oxide, and corresponding four-membered ring as trimethylene oxide. Interestingly, systematic nomenclature has several names for this compound. It's called oxirane, epoxyethane, or oxocyclopropane. And oxirane and oxocyclopropane are in general used now. For four-membered ring, trivial name, as I mentioned, is trimethylene oxide, and systematic names are oxetane or oxocyclobutane. You should know all of these names. So, after the simplest member of the homologous series, all of the epoxides are called oxiranes. So after oxirane, all of the compounds, ethers that contain cyclic three-membered ring with one oxygen as ring atom are called oxiranes as systematic name, or epoxides as trivial name. Oxiranes or epoxides are highly reactive because of the angle strain and torsional strain in a three-membered ring. So they readily undergo ring opening reactions with typical reagents, typical electrophilic reagents. For example, hydrogen chloride. First step is slow protonation step to give oxonium ion, and then in a second step, backside attack in SN2 type reaction is fast step to result in open chain product. Epoxides are highly reactive compared to ethers because they are unstable. They have high energy content. They are unstable because they are three-membered rings. That means they have high angle strain and high torsional strain. Compared to ordinary open chain ethers, when we consider reaction pathways, reaction diagrams, energies of transition states and energies of the final products are about the same. And so in those aspects, they don't differ. What they differ is in that epoxides are highly unstable, while open chain ethers are very stable compounds. And because of the high energy content of the high strain, high torsional strain and high angle strain in epoxides, activation energy needed to reach transition state, which otherwise would be relatively high, but energy to reach transition state is relatively low. Only small activation energy is needed to reach transition state, and then reaction readily proceeds. So, epoxides readily react with typical nucleophiles in ring opening reactions. If nucleophile is charged, carries negative charge, as in these examples, then second protonation step is needed to protonate oxygen so that alcohol is the final reaction product. In the first case, we have a reaction of sodium phenylthiolate, and then followed by protonation step. In the next reaction with cyanide anion, for example, potassium cyanide, again followed by protonation. And in the final step, reaction with sodium azide, again followed by protonation. And you can see in each case an open chain product is obtained where we get an alcohol that has substituent on beta carbon, and corresponding nucleophile is substituent now on the beta carbon. Here are some additional examples. In this case, with nucleophiles that are not charged. Of course, when nucleophile is not charged, then there is no need for second protonation step. Proton transfer will result in protonation of oxygen to give the final product, alcohol product, as in this case, in this example, formation of amino alcohol. And here is another example of formation of a different amino alcohol, reaction with methyl amine. So in this case, it's secondary amine that is the reaction product. Reactions with alcohols gives alcohol ethers. And this is an interesting example, ring opening of epoxides to give alcohols. So you have already seen hydride as a nucleophile, that lithium aluminum hydride and sodium borohydride serve as reagents that are sources of hydride nucleophile. Only lithium aluminum hydride in general is suitable reagent for ring openings of the epoxides. In general, sodium borohydride does not work well. So lithium aluminum hydride results in addition of hydride anions from the backside to open epoxide ring and to give alcohol as reaction product. And then we have some other examples, for example, formation of diols, simply by ring opening of epoxide with water, in this case under acidic conditions, and reaction with non-charged sulfur nucleophile, so reaction with diols. Reactions of nucleophiles with an epoxide are regioselective, which means that when two carbons of the epoxide ring are different, then there is selectivity in reaction of nucleophile with them. And selectivity depends on whether reaction is carried out under acidic or basic conditions. Even though both under acidic and basic conditions, reaction mechanism is SN2, regioselectivity differs on whether reaction conditions are acidic or basic. Under acidic conditions, somewhat unexpectedly, nucleophile adds to more substitute carbon. The reason for it is that intermediate is oxonium ion, and in the transition state, carbon of the epoxide ring that interacts with nucleophile develops partial positive charge. So it looks a bit like carbocation. So more substitute carbon better tolerates developing partial positive charge or developing electron deficiency, and for that reason, such transition state is lower in energy and preferred reaction pathway. Less substitute carbon, of course, doesn't tolerate positive charge very well, so that would be higher energy pathway. So under acidic conditions, nucleophile adds to more substitute carbon. This first case actually is not a very good example because the two substituents end up being both hydroxyl groups. So that's not a very good example to distinguish between incoming nucleophile, incoming OH group, and the existing oxygen. But you can see that nucleophile adds to more substitute carbon. In the second example, we have methanol as a nucleophile, and that's a better example because methanol as a nucleophile adds to more substitute carbon of the epoxide ring, and as you can see here, and product has ether oxygen on more substitute carbon and hydroxyl oxygen, alcohol oxygen on less substitute carbon. So in summary, when reaction is carried out under acidic conditions, in each case nucleophile attacks the more substitute carbon which carries larger partial positive charge. Under basic conditions, reaction is typical SN2 substitution and reaction proceeds as expected with nucleophile attacking less substitute carbon. So less sterically heated, less substitute carbon. So bond is formed to less substitute carbon. And so here we have an example, first example where nucleophile methoxide anion attacks less substitute carbon and the final product ends up with ether group being on less substitute carbon and alcohol on more substitute carbon. In second example, the same methoxide anion attacks less substitute carbon, less sterically hindered carbon, and corresponding product is obtained. So first example, as you can see, attack on less substitute carbon, and second example, again, attack on less substitute carbon. So it's less hindered carbon that is attacked under basic conditions. Opening of epoxide ring is also stereoselective. That's a consequence of the reaction mechanism. Reaction mechanism is SN2, that involves backside attack, and that means that, of course, reaction is stereoselective. That's best seen when products are cyclic, and that is the case when epoxide ring is fused to another ring, typically 5 or 6 membered ring. Those are the best examples. And here we have an example where epoxide is fused to a 6-membered ring. So backside attack of nucleophile, in this case bromide anion, of course involves ring opening, and upon protonation, 2-bromocyclohexanol is formed. Note that reaction product is diaxial, as you would expect from the reaction mechanism. Of course, product is trans, so product is trans 2-bromocyclohexanol, and in case of trans 1,2 disubstitute cyclohexane rings, it's di-equatorial conformation that is more stable. So this 6-membered ring will flip into alternate chair to give di-equatorial conformer. That's the more stable one. But sometimes ring flip is not possible, And that's, for example, the case of transdecalin. So transdecalin involves two fused six-membered rings. They are fused in trans stereochemistry, and so ring flip is not possible. That fusion prevents ring flip. So then, if epoxide ring is also fused to a decalin system, then ring opening results in trans diaxial product, which remains in diaxial conformation simply because it cannot flip into di-equatorial. And here are some additional examples, and in each case, as a result of backside attack, product is always trans. So as you can see, you can pause the video here and examine each example, but regardless of the nature of the nucleophile, regardless of what is the nucleophile, the attack is always backside attack, which means that product is trans product. Analysis of stereochemical outcome of simple epoxides that are not fused to another ring is a bit more complex. It may help our analysis if we draw epoxide vertically, so that carbon-carbon bond of the epoxide ring is vertical. And then we can do attack of the epoxide from the backside, and with appropriate rotation we can easily come up with suitable Fischer projections of the reaction products. So we can see that a reaction of trans epoxide with a nucleophile results in formation of erythro product, or if all substituents on each of the karate center are identical, meso compound. And reaction of cis epoxide with a nucleophile results in formation of trio pair of enantiomers. This completes our study of reactions of ethers, and next we are going to look at reactions of sulfur and nitrogen compounds.